Welcome, welcome, welcome. Hope y'all are doing all right. Let's get things up here. Oops. There is the usual link to the attendance form. Go ahead and fill it out when you have a chance. Let's see, let's wait a minute, see if everyone gets here. We'll give it a minute and see if a couple of people show up before we start going here. Just a reminder, today is the day we will focus more on Nimdari's class. So if you're in his class, you are prioritized and you get to ask your questions first. And if you guys don't have any questions, it's a free-for-all. Get the black dust all over my glass here. The one downside of the whiteboard is it's definitely the pens. Pens are not great, although chalk is terrible too. So yeah, it's damned if you do, you're damned if you don't. All right, it's 11:01. Man, yeah, black dust. It's a plague. Sorry, my lips are a little chapped. Okay. What did I want to ask? Oh, a couple things. So I will have office hours today for those of you that want to ask questions there, although I feel like our class is kind of like office hours anyway. Like you guys can just ask questions. I don't really have stuff to present necessarily, but I can certainly try to. Okay, if you guys send me questions ahead of time, I'm certainly happy to try and make stuff up and come up with examples for you all. But I wanted to say, so there's office hours today from 1:30 to 2:30. I posted an announcement in Canvas, and there's a link to the Zoom meeting there. The password is the same as the password for the class, which is Newton. And what else? As far as the participation points of the class, and I'll write this somewhere in Canvas or put it on the Google assignment somewhere. Since I'm only requiring essentially that you attend one class per week, right? Because if today you're in Whitener's class, you don't really have to be here if you don't want to be, and vice versa. If on Tuesday and you're in Nimdari's class, you don't want to show up, that's perfectly fine, although everyone is welcome. Excuse me, I decided to make the attendance for class sessions worth 4 participation points instead of 3, which won't get you to the weekly 6. But even if you only attended one class a week and did the weekly quizzes, which you get 100% on just for doing, if you only did that, you would still pass the class. So again, don't worry about this class. The intent is everyone passes as long as you're participating, showing up, doing stuff. Also, I will update the Google assignment form to include that you get 1 point for attending office hours if you attend office hours. So maybe 2, I don't know. Yeah, maybe I'll make it 2, just so then you can attend an office hour and a class and still get all the 6 points. Yeah, this is a better idea. Good job, James. Again, don't sweat the participation points too much. As long as you do stuff, you should be fine. I think that's all I had. I was kind of looking at the Nimdari handouts and stuff, but I feel like there's just so much content to digest that I'll be perfectly honest, there's a lot of content to digest for all the classes I'm trying to help. And unfortunately, I feel like this one's kind of getting the short end of my focus. So I am not as good at knowing what's going on in this class. So it's going to be kind of on you guys to have questions to ask me. So do you guys have any questions? Or anything you'd like me to talk about? Probability mass function. Yes, although I think I usually call it, I think I'm more familiar with it being called the probability density function. Yeah, spelled function wrong, but you know, that's right. Yeah, so let me ask you first, are we talking discrete or continuous? Not that we can't do both, but is there one you would like me to start with? Okay, discrete. Certainly. Let me grab some examples that I definitely kind of have ready to go. 1 second here. Not you. Sorry. I've got like a million things to pull from, but you know, it's hard to keep track of all of them. Sure. Okay. Sorry, let me make this a little bit. So probability density function is just a way of describing the probability with which things happen. So, gosh, that tape is real small. So let's say we had something like this where that pen is not the best. Let's use my good blue pen here. We'll say X is a discrete random variable. And I'll try and give some context for this in a minute, but we'll write, and the probability that capital X is equal to some number, which often we use this kind of notation, the probability that capital X is equal to little x, which I know feels kind of dumb, but what we do. This is we also write this as the little p of x is given by the following table. So x can be 1, 2, 3, 4, 5. And the numbers are just going to be kind of made up. The probabilities are 0.3, 0.1, 0.1, 0.27, and 0.23. Okay. And so here is where we have to kind of be maybe imaginative, because like, what is x? X is a number, 1, 2, 3, 4, 5. You could imagine that maybe x is, so maybe you've got like a giant vault. Vault's not the word I was trying to say there. Maybe you've got like a giant bucket and it's filled with all sorts of balls of different colors. We often use examples of balls of different colors. Or maybe socks. How about socks? Let's say you've got a box full of millions of socks, because why not? And let's say there are blue socks, and there are red socks, and there are white socks. And here, X is the number of blue socks you pull out. So let's say X is the number of blue socks. So I reach in, I grab 5 socks, and X is the number of them that are blue. And these happen to be the probabilities with which you pull out blue socks. Okay, kind of a weird example, kind of weird makeup, whatever. So when you have a discrete, a probability density function, like we have here, all that means is that you can say, well, okay, I mean, literally we have a table here. We can use these values to determine different things. For example, what's the probability that X is equal to 2? Well, that's going to be 10%. Right? There's not, I feel like this table isn't doing a lot for us. We'll see another example in just 1 second here. A couple things to know about probability density functions. So, a couple things to know. The probability of any one thing happening should always be greater than or equal to 0. It should also be less than or equal to 1, right? You can't have something happen with negative probability. You can't have something happen with greater than 100% probability. The other thing to know is that all the probabilities add up to 1. Oh, my slipper just came off. Ah, come on, slipper. Sorry. Or sum to 1. Right? What's the probability that, oh, so, I feel like my table is not really good for my example because I left off 0. So, oh well. Right, so maybe I can change my table a little bit to be more inclusive. right? Because you could pull out 0 blue socks if we're imagining 0 blue socks. So I'll make this 0.15, and then I'll make this 0.15 as well, so they still add up to 1. Let's actually double check that. 0.3, 0.4, 0.5, 0.67. Oh, I think that adds up wrong. No, I made a mistake. 0.15 plus 0.15 is 0.3 plus 0.1 is 0.4, 0.5, 0.77. I said 6, 7 last time, and then 1. So your probabilities should be between 0 and 1, and they should all add up to 1, and they do. 0.15 plus 0.15 plus 0.1 plus 0.1 plus 0.27 plus 0.23 definitely equals 1. Or you might see this written as the sum of, how do we usually write this? I equals 1 to n of p of x of I should equal 1. That's often how that gets written. So let's look at so there's more I should say about this actually. There's a related topic called the CDF, or the cumulative distribution function, which you may or may not. So have you guys heard that said? Cumulative distribution function? I'm sorry, cumulative density function. Yes, no, okay. It's fine if it's no. If you guys do, oops, sorry, I turned off the chat. If you guys do see it later on, let me know. We can definitely talk about it. It's not too much more challenging than this what we're talking about here. But then we can use this table to answer all sorts of questions, like what's the probability of getting, and so here's actually a good way of asking this question. What's the probability of getting I was going to say something smart and now I've lost it. Sorry, my brain. Of getting at least one pair of blue socks. It's actually not a bad question. Maybe. He said self-congratulatory. So what does it mean you get a pair of blue socks? Well, it means we have at least 2. We could have 2, 3, 4, or 5. So that probability would be the probability that x is greater than or equal to 2, which would just be the probability of 2, 3, 4, and 5. So you could do it this way. It's a little p of 2, it's a little p of 3, it's a little p of 4, it's a little p of 5. And then you just add those up. So 0.1 plus 0.1. You guys are rattling around too much. And then that's something, right? It's 0.70, I think. This, although, so you can definitely do it this way. This might be an example though, where it's actually easier to calculate the complement. So instead of saying, what's the probability that x is greater than or equal to 2, I could instead ask, well, what's the probability that x is less than 2? So if I'm strictly less than 2, it means I'm not equal to 2, right? I don't want to get 2 socks. So that'd be the probability that x is 0 plus the probability that x is 1, which is just 0.15 plus 0.15. So then the probability I'm actually trying to calculate, the probability that x is less than or equal to 2, is just 1 minus the probability that x is greater than 2. Sorry, I got those backwards. Probability that x is greater than or equal to 2, excuse me, is 1 minus the probability that x is less than 2. And which is 1 minus what we just found there, 0.3. Oh yeah, that's 0.7. Okay, so let's look at another example. Look at, and this is a common example. We talk about flipping coins. 3 coins, we could do 3, we could do more. So I want to know, so I have to be a little more specific here. We're going to let x equal the number of tails that come up when you flip 3 coins. So there are 4 possibilities. You can get 0 tails, 1 tail, 2 tails, or 3 tails. And I want to find the probability of each of those things. So what's the probability of getting 0 tails? Well, there's a couple ways you can do this. One way is to list out everything. You can say, well, if I've got coin 1, 2, and 3, I can have tails, tails, tails. I can have, so that's 3 tails. Then there's a couple ways of getting 2 tails. I can have tails, tails, heads, tails, heads, tails, heads, tails, tails. Those are all the ways of getting 2 tails. That 3 tails. And I can also have tails, heads, 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 tails, heads, 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 tails. Those are all the ways of getting 1 tail. And then finally, all heads. So there are 8 possibilities. Each of them have equal likelihood. So the probability of getting 0 tails is exactly 1 way out of 8. Another way you could calculate that is by saying, well, what's probably the first one is tail? 1/2, or sorry, not a tail, head 1/2 times 1/2 times 1/2 is 1/8. Now it's not the same calculation for this one though. So what's probably getting 1 tail? Well, there's exactly 3 ways. So 3 out of 8. 2 tails, also 3 out of 8. 3 tails, 1 out of 8. So here is the probability density function for this variable where we flip 3 coins and we ask how many tails show up. And we could ask ourselves something like, erase this. What's the probability of flipping at least 1 tail? Well, again, you can add, so when you have this table, it's pretty easy. But like, well, it's 1, 2, or 3. So this plus this plus this is 7/8. You can also calculate it via the complement. It's 1 minus the probability that x is less than 1. Which, well, if it's less than 1, right? If you're less than 1, you're not equal to 1. So be careful, right? Especially with these discrete variables. If you're doing the complement of greater than or equal to, it's got to be strictly less than. If you're doing the complement of greater than, it's got to be less than or equal to. So that you always get the number that you're looking at included in one of the sections, but not both of the sections. So this is just 1 minus the probability that x is less than or equal to 0. Instead of 1, I wrote p. But that's 1 minus 1/8, which is 7/8. So either we get the same thing here. Knowing these values is not too terrible, but it can be kind of a pain to have to make that table. For 3, it's not so bad, but what if I have something like 7 coins? So in fact, actually, I think that's a good place to go. 7, well, let's do 6. 7's a little large. So same idea. Now we're flipping 6 coins. And unless someone says otherwise, we're making the usual assumption that it's a 50-50 chance of flipping a heads or a tails. So, right, 6 coins that are fair coins. X is going to be the number of tails. And I want to know what's the probability that the number of tails is 4. Well, here's the thing. It's really a giant pain to list all the ways that you can flip 6 coins. Because the number of ways, the number of possible outcomes is, well, there's 2 outcomes for each coin. There's 6 coins. So the number of possible outcomes is 2 times 2 times 2 times 2 times 2 times 2, which is 2 to the 6th. Wow. Amazing how you can say one thing and think it and write the other thing, which is 64. And although it's not impossible to write those all out, it's certainly not fun. More importantly, it's not necessary. So this is kind of an example of a binomial distribution where you have another way of calculating the probability of something happening. So I want to know what the probability of being 4 coins is. So, 4 tails. So here's the thing. That's going to be, there's 3 things to think about here. The number of ways to get 4 tails out of 6 coins. Which you might just argue is the thing we need, and in this example, it kind of is. Right? If you knew the number of ways you could get 4 tails, you would just say it's that number divided by 64. And that would totally work when you have something that's nice and symmetric like this. But it would change if it was an unfair coin, which we'll look at next. So how do you find the number of ways to get 4 tails without listing them all out? Well, there's this wonderful function. It's called the choose function. And in the calculator, it might look like this, like NCR, or it might look like this, where you have parentheses and an N over an R. It's not a fraction, it's just an N over an R, where N is the total number of things you're picking out of. So total, which in this case is 6, and R is the number of things you want. So in this case, R is 4. So I want to know what 6 choose 4 is. I might have picked numbers that are slightly too big, but whatever. So, I mean, not because they're not. So here's the way you calculate N choose R. N choose R is equal to N factorial, which is just N times N minus 1 times N minus 2 all the way down to 1 over N minus R factorial times R factorial. So in this case, 6 choose 4 is 6 factorial over 4 factorial. Sorry, I mean, it doesn't really matter which order, but technically the 2 is the one that's first. Over 2 factorial times 4 factorial. So here's what this looks like. 6 factorial, and I'm going to write it out. It's 6 times 5 times 4 times 3 times 2 times 1. 2 factorial is 2 times 1. I kind of ignore the ones usually, whatever. And 4 factorial is 4 times 3 times 2 times 1. And these will cancel. So I'm up to 6 times 5, which is 30, divided by 2, which is 15. So there's exactly 15 ways of getting 4 tails and 2 heads. And I'm going to list them for you because I do think it's worth seeing kind of how this works. So there's a method to this madness. When I'm writing this out, I'm actually going to think about where the heads go because it's easier to keep track of 2 things versus 4 things. So I'm going to start with my heads at the very right. So I'm going to have 4 tails, 2 heads. And then I'm going to let this one move over to the left while I keep that other one there. So I'm going to have, right, it moved over one spot. It's going to keep moving. Moved over again to the 3rd spot. Now it's going to move over to the 2nd spot. Now it's going to move over to the 1st spot. Okay, that one's moved as far over as possible. So I'm going to go back to the beginning and then put a tails in the right spot here. So yeah, I think I can fit it all. I'm going to fit it in over here. So then I'm going to go over here and have, okay, I'm going to have tails in the rightmost spot and then heads, heads, tails, tails, tails. And then again, I'm going to keep this one stationary and let this other one move over. So I'm going to move it over 1. Then move it over again. Again, and I'm done. Again, this one stayed in the same spot the whole time. Just like, sorry, I circled the wrong one. This one here. This one stayed in the same spot the whole time. And I let the other one travel over. So I'm not repeating anything, right? I want to make sure I'm not double counting how I can get 2 heads and 4 tails. So, right, these examples are the first coin is tails, second coin is tails, third coin is tails, fourth coin is heads, fifth coin is heads, sixth coin is tails. So then I keep doing the same thing. I'm going to look at now this. Tails, tails, heads, heads, tails, tails. And then we keep this heads in the 4th spot stationary. We'll let this one travel over. Tails, heads, tails, heads, tails, tails. And then travel over. Heads, tails, tails, heads, tails, tails. All right, let me make sure these don't look like they're running into each other. Okay, got 3 more to go, I think. So I've exhausted the heads being in the 4th spot there. So I'm going to move it over to the 3rd spot and have tails, heads, heads, tails, tails, tails. This one's going to stay stationary, not for very long. I'm going to move this one over. And then finally, I've exhausted that. So then one more is just heads, heads, tails, 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 tails. All right, and that's all. And how many are there? 15. So the point of all that is you don't have to do that work. If you want to know how many ways there are getting 2 heads and 4 tails, it's just out of 6 coins, it's 6 choose 4. And the choose function literally counts the number of ways you can pick 4 things out of 6 distinct things. So another way I could phrase that is if I had a group of 6 people and I wanted to know how many different 4-person committees could I make out of those 6 different individuals, there are literally 15 different committees that I could have that had 4 people on them. So that's what the choose function is. All right, so this is going to be 15. Again, we were finding the probability of getting x equal to 4 tails. There's 15 ways of getting 4 tails. But then the probability of getting 4 tails, or like the probability of getting tails 1/2. So you're going to have a 1/2 to the 4th, right? That's the 4 tails, and then a 1/2, or some people write 1 minus 1/2, because this is your probability, and this is 1 minus your probability. It's the leftover. That's going to be 1 minus 1/2 squared. This is going to look like 15 over 64 because it is, right? It's 15. 1/2 to the 4th is 1/16. 1 minus 1/2 is also 1/2. Squared is 1/4. And I get 15 over 64. Which I don't think is too terribly surprising because, again, for this particular distribution, there are 15 ways of getting 4 tails and exactly 64 different things that can happen. So 15 out of 64 makes sense. Sorry, my voice is starting to. You guys are kind of like in the worst spot for my voice because like you're usually kind of at the end of my day of a lot of talking, so you get Horse James more than other people do. Yeah. So this is an example of a binomial distribution. Yeah, I want to say that. Let's change up the example a little bit. Yeah, I'm going to leave this here. We're going to do this. So let's say we had an unfair coin. Let's say we had an unfair coin, or 6 unfair coins that had a probability. So for our unfair coins, the probability of the tail is going to be, let's say it's 2/3, and the probability of a head is 1/3 for each coin. And I think, I should use different notation here, right? They typically say like, I think they use like, for a tail, little p is 2/3, and then for a head, the complement of the other thing, little q is 1 minus p, which is 1 minus 2/3, which is 1/3. And now I want to know, same question, what's the probability of flipping 4 tails? And for this one, with something unfair like this, we can't just count up the number. I mean, we still need to count the number of ways, but it's not sufficient to count the number of ways to say, oh, well, there's 15 different ways of getting 4 tails. There's 64 total possibilities, so 15 out of 64. That is no longer correct because it's not symmetric. We don't have the same probability for heads and tails anymore. So here's how this calculation works. It's pretty much the same as before. It's the actually, let me look at one thing real quick, just because I want to make sure that I'm saying this the way I mean to be saying it. Which, of course, I can't actually find the thing I'm trying to find. Nope, just kidding. It's here somewhere, but Oh, actually, I think I do know where it is. One sec. I just want to make sure I'm telling you guys the right things. Okay, whatever. Yeah, sure, definitely, Kimberly. So, let's do it. So for this one, the probability that x equals 4 tails is going to be equal to 6 choose 4, the number of ways you can choose 4 tails, and then the probability that you get a tail to the 4th power, because we want 4 tails. And then, well, if you want exactly 4 tails, the other 2 have to be heads. Then you get heads with 1/3 probability. So that's how you calculate this one. Yeah, we'll definitely talk about the variance and stuff in a second here. So this 6 choose 4 is still 15. And now I'm going to get 2 to the 4th over 3 to the 4th times 1 squared over 3 squared. This ends up being 15 times 2 to the 4th. So the numbers don't really matter at this point. We should still calculate it, but you get 15 times 2 to the 4th, which is 16, divided by 3 to the 4th times 3 squared, which is 3 to the 6th. I think I can cancel 1, 3, right? 15 has a factor of 3 in it. It's getting loud in there. That was exciting. So I got 5 times 16, which is 80, over 3 to the 5th, which is 243. So the probability of getting exactly 4 tails with this unfair coin is 80 out of 243, which is about 1/3. And we could actually calculate it. I have a calculator. So 80 divided by 243 is about 0.33. So very close. I'll say 0.329 just to make sure you guys are like not exactly 1/3. Whereas on the other side here, this probability of getting 4 tails with a fair coin would be, where'd you go? It was 15 out of 64, which is about 0.23. So obviously very different, which we would expect if the coins have a different probability of if it's a fair coin versus an unfair coin. So let's actually in both of these contexts talk about the expected value first, and then the variance we should be able to talk about as well. So again, when I say the words expected value, you should hear me say average, because that's all I really mean. When I say what's the average, what's the expected value, I mean what's the average. So if I flip 6 coins again, what's the expected number of tails? Well, if it's a fair coin, the answer is actually really easy. The expected number of, and watch, even if it's unfair, the expected number of tails is exactly the number of trials, or the number of flips in this case, times the probability of getting a tail. And I'm just going to say, I apologize for my notation. I'm sure it's not exactly what you guys are writing, but I'm not great with the notation with this, so I apologize. I will try to make it better, but it's always people do different things. So here the number of flips is 6, and if it's a fair coin, the probability of getting a tail is 1/2. So that's going to be 3. So this is the easy way to calculate it. Same thing on the other side, actually. If I have, so I happen to pick nice numbers, lucky me. If I have a coin that flips the tails 2/3 of the time, and I'm doing 6 flips, well, the expected number of tails would be 6 flips times 2/3 probability of getting a tail, which is going to be 4. Now, the actual calculation is a little more complicated, but it actually always works out this way. Which is why we call it the expected value, right? I mean, literally using the words, if I flip 6 coins, I would expect generally that half of them would be tails and half of them would be heads, which would be 3 and 3. Now, the way you can calculate the expected value, and I'm going to call it expected value, sure. Well, it's the usual way. It's the weighted mean. It's the probability. It's the values times the probability. So, So there are 7 different things that can happen. I can have 0 tails, 1 tail, 2 tail, 3 tail, 4 tails, 5 tails, 6 tails. And it's going to, what I'm going to calculate here is it's going to be, sorry, brain. The number of tails, x of I, times the, maybe this should be x of I equal to that. No, sorry, again, notation is less than excellent here because my brain doesn't want to work right. Sure. Let's just call it that. Sorry. There. Okay. Now we're going to do this calculation, but it's going to come up to be what we already thought, which is going to be 3. So, I don't want this anymore. So I can get 0 tails. What's the probability of getting 0 tails? Well, 1 out of 64. There's exactly one way to get 0 tails, all heads. Okay, and then I have 1 times the probability, 2, 3. I just want to make sure I have enough room. Also, the nice thing about this calculation for a binomial distribution like this is it's actually symmetric. So if there's if there's 1 out of 64 ways of getting 0 tails, there's also 1 out of 64 ways of getting 6 tails, right? Because there's only one way to get 0 heads or 6 tails. All right, what's the probability of getting, 1 tail? Well, this is just the choose function again. If there's 6 coins, there's exactly 6 ways one of them can be a tail. First one, second one, third one, fourth one, fifth one, or sixth one. So there's 6 out of 64 ways you can get 1 tail. That 6 is just 6 choose 1, which is 6 factorial over 1 factorial times 5 factorial. Okay, how many ways are there of getting 2 tails? 6 choose 2, which is just 15 over 64. How many ways are there getting 3 tails? 6 choose 3, which I don't know off the top of my head. I want to do that one because we did it before. Actually, that's not choose. When you use choose 2, it's pretty easy. Choose up the numbers. So this is going to be 6 factorial over 3 factorial times 3 factorial, which I always like to just write out 6 times 4, 5 times 4 times 3. 1. 3 factorial is 6. 3 factorial is 6. Cancel, 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 cancel. 5 times 4 is 20. And then we have symmetry. If you can pick, if there's 15 ways of picking 2 tails, there's 15 ways of picking 4 tails because there's 15 ways of picking 2 heads. If there's 6 ways of picking 1 tail, there's 6 ways of picking 5 tails because there's 6 ways of picking 1 head. All right, so now for the big reveal. Let me make sure I'm not screwing something up here. So this should come out to 3. Let's double check. So we've definitely got divided by 64. So I'm expecting the top to come out to be 64 times 3, which is 192. Okay, let's see. So I get 1 times 6, plus 2 times 15, plus 3 times 20, plus 4 times 15, plus 5 times 6, plus 6 times 1. And the symmetry here is probably by design. I end up with, let's see, 60, 120, 180, 192. So that's how you, so again, you don't have to do this calculation. I don't really want you to do this calculation, but I want you to see that you can get the expected value the long way by doing the values multiplied by the probabilities all add up together. But you can also do it the short way by just saying it's the number n of trials times the probability. It works for dice too. Should I do this example first? I don't know. Gosh, I don't really want to do this. So do we do the same sort of thing here? It'd be I mean, I guess it's not terrible. We've essentially already done the work. So the only difference here between this and this is that our probabilities are different, right? It's no longer 1/64 and 6 right? So okay, fine. I convinced myself I'm going to do it, even though I don't want to. Yeah. So again, if I want to find the expected value of the number of tails, it's going to be the sum of the number of tails times the probability of getting that many tails. So it's the sum x equals 0 to 6 of x times the probability of x. Okay. Sorry, I have to make sure something about this right. So again, it's going to be 0 times something plus 1 times something. All right, so what's the probability of getting 0 tails? Well, it's different than last time, right? Because last time, so the previous one, probability of getting 0 tails is 1 out of 64. And you can think of it as, you know, there's a 1/2 times 1/2 times 1/2 times 1/2 times 1/2 times 1/2 6 times. Here it's a little different, right? Probably getting 0 tails is now it's going to be, well, getting 0 tails and getting 6 heads. So the probability of 0 tails is 6 choose 0. Right? There's one way of getting 0 tails times, let's see, tails is a probability of 2/3. It's 2/3 to the 0th, and then 1/3 to the 6th. That's a 1. So this is going to be 1/3 to the 6th. Probability of getting 1 so this gets more complicated because I picked a complicated example. Probability of 1 tail is 6 choose 1 times 2/3 to the 1st times 1/3 to the 5th. So here's what I'm seeing for each of these calculations. In each of these, I'm going to get something divided by 3 to the 6th, right? Because I'm always going to get something over 3 to a power and something over 3 to another power, and those powers are always going to be 6. So I'm going to have, let's see, in this case, I'm going to have a 6 choose 1 times 2 over 3 to the 6th. Gross. Okay. The next one is going to be, no, that's right. Okay. Next one's going to be 6 choose 2 times, so then it's going to be right 2 squared times 1/3 to the 4th. So I'm going to get a 2 squared over 3 to the 6th. So I'm pretty sure the power is going to continue in this way. The next one's going to be 6 choose 3 times 2 cubed over 3 to the 6th. and then 6 choose 4 times 2 to the 4th over 3 to the 6th. So, by the way, the point here is you shouldn't do it this way. 6 choose 5, 2 to the 5th over 3 to the 6th. 6 choose 6, 2 to the 6th over 3 to the 6th. Okay. So hopefully this calculation is not too gross. Let's check it out. I'm going to put my 3 to the 6th in the denominator because I know that each of these has a denominator 3 to the 6th. Here my numerator is 1. Here I get 6 times 2, which is 12. Here I'm getting 2 times 6 choose 2, we already know is 15. 2 squared is 4. That's 60 plus times 2 is 120. Plus, I'm really nervous this is going to turn out wrong, but I think it's going to turn out right. 6 choose 3, last time we saw was 20. So I've got 3 times 20 times 8, which is 8 times 60 times 8 is 480. Oh, I'm worried. Okay, 6 choose 4 is also 20. So you've got 4 times 20 times 2 to the 4th. So you've got big numbers. That's 320 times 4 is 1280. Maybe it's time to use a calculator. Calculators are good. There's nothing wrong with a calculator. Double check my work. 4 times 20 times 16. Yep, 1280. Finally, we have 5 times 6 choose 5 is 6 times 2 to the 5th is 32. That's 30 times 32, which is 960. And lastly, we have 6 times 6 choose 6 is 1. 2 to the 6th is 64. So 6 times 64. All right, and now here's where we cross our fingers. We are hoping to get 4 as our answer. So I'm going to add at the top 1 plus 12 plus 120 plus 480 plus 1280 plus 960 plus 384. Divided by 3 to the 6th. And then I'm worried. I made a mistake somewhere. I got 4.44. Well, the answer should have been 4. I clearly must have made an error somewhere. And I don't feel like I should go back and check, even though I really want to. Like, really want to. I see. No, I don't see it. Sorry, you guys. This is what happens when you make things up on the fly. 3, 6 choose 3. 8. Sorry. 4, 20, 16. Oh. Let me double check. Mm-hmm. I don't know. It bothers me so much. Oh, well, I see one mistake I made. This should be 0. 0 times some stuff is 0. I don't think that fixes the problem, though. Let me just double check one more time. See if I can be good about this. I know we're just about out of time, aren't we? Yeah. So hopefully you guys felt like today was valuable. If you didn't, I apologize. I'm off by some amount. I'm off by 320, which is a good sign because that seems like a number that I can easily be off by. How am I off by 320? 0. 1 times 6 times 2 is 12. 2 times, that's definitely 15. Times I don't know, guys. I made some dumb mistakes somewhere, and it's just gonna have to live in my soul, I guess. Anyway, so the short answer to your question, Kimberly, which I know I spent a lot of time answering, is that you can calculate the expected value by just multiplying the number of trials by the probability. So for example, one last example is if you roll a 6-sided die, what's the expected value? Well, there's 6 sides. And I'm sorry. If you take, so, oh gosh, sorry. It's 1/6 of the sum. It doesn't feel like what I was saying before, which is just 1/6 of 21, which is 7 halves, which is 3.5. And I know there's a way to think about that, but now I'm not seeing it right off the bat. I think it's different with coins. All right, I'm going to think about this some more, but I don't want to waste your guys' thought. But I don't want to keep you any longer than I should. So I'll try and figure out why my answer was a little bit off. I'm sure I just made a dumb arithmetic error that I'm not catching. And yeah, I have office hours from 1:30 to 2:30. You all are welcome to come, and definitely come with questions, because otherwise I don't necessarily have content just to make up right off the top of my head. So come with questions. All right, I'll see you guys later.